So what you're looking at here is a simply supported beam, and we're going to draw the shear force diagram and the bending moment diagram. So let's begin. So to draw the shear force diagram or the bending moment diagram, we first need to find the reaction forces at RA and RB. Now to do this, we're just going to use our system clockwise moment equals counterclockwise moment. And in case you don't know how to do this, you can watch this next video that I'm going to pin right here and then come back to this one. But I'm going to go through relatively quickly on this, but in case you're missing the point, then please watch this video and then come back to check this one out. So to find the reaction forces, we're just going to set up our system with clockwise moment equals counterclockwise moments. And in case you don't know what's happening here, then I've done another video which you should see appear in the top right corner now, or check it out in the description, and that breaks down everything I'm doing in full details. So I'm going to go through this here relatively quickly. So we should have our 5 times 4 plus 19 times 7 for our moments, and then finally our 8 multiplied by our 16. All of that equals RB times 20. So then just to go through the answer real quickly, RB would be equal to all of this bit summed. So what that looks like should be 281 divided by 20, and that equals 14.05 kilonewtons. So we have our RB, and then to find RA, we're just going to take the vertical forces, should be balanced. So everything that's going down, when we add them up, so 5 plus 19 plus 8, and we're taking away that 14.05, that's going upward, and then we're left with our answer for RA, which is 17.95. 17.95 kilonewtons it is. So that there represents our reaction forces. And what we're going to do now, we're going to draw our shear force diagrams now that we know what the reaction forces are. So I'm just going to write in the values here for the reaction forces, which turns out to be RA 17.95 kilonewtons and RB 14.05 kilonewtons. So that's it, the shear force diagram. We're going to draw that now. So for the shear force diagram, I am just going to draw a set of vertical lines that will represent the points where the forces are acting at. So that's my diagram done. And all I'm going to do now is to label my axis. So over here to the vertical axis, that's going to represent my shear forces. So I'll just put SF for shear forces, and along the horizontal line, that's going to be representing my length of the beam. So now all that's left for me to do is just to plot the points and do the diagram. So what that looks like, I'm going to start by plotting the points first, and then we draw the diagram and put everything together. I'm just going to use a red highlighter to mark the points. So the first point, I'm going to start from the reaction at A. So that means the first point will be plotted right here at right there, around about 17.95 on that first line that we drew. So then when we go across now, we can see that we're going to go down by 5. So from 17.95 going down by 5 kilonewtons, then that's going to leave us at 12.95. So the next point is estimated around there. Let's say that point there is 12.95. So from 12.95, we're going to go down by 19. So that's going to take us to 6.05, somewhere around here. Then from that 6.05, we're going to go down by 8 once again. So that's going to take us down to 14.05, somewhere around here. And then from 14.05, we're going to go across to our reaction, and that's now going to take us all the way up back to our start point right there. So all we're required to do now is just to connect the lines. So I'm going to do that now. So the first line is going to go across from RA to that 5 kilonewtons. Then from the 5 kilonewtons, we're going to go down now to that 12.95. Then from the 12.95, we're going to go across to the next force at 19 kilonewtons. So now we need to go down to the negative 6.05 and across to the 8 kilonewtons. And then we go down to that negative 14.05, across to RB and back up to 0. If you want, you can always make it look fancy, shade in the bit that we have interest in. So that's our shear force diagram. It's what it should look like. It's a technique that you can apply to do your shear force diagram. So now we're going to go into finding the bending moment calculation so we can do the bending moment diagram. So the bending moment does require calculation. So we're going to do our bending moment calculations, and after we do them, we just need to plot those points. So for the bending moment, we're going to use this one formula again, which is force multiplied by perpendicular distance. And for this one, you have to try and use your imagination. So as I go through, you should see exactly what point on the beam I am talking about. So for the bending moments, we have to do our bending moment calculations. And that's what we're going to get into now. And once we finish with those, we just need to literally plot those points. And to do the bending moment calculations, we're just going to use this formula to find the moments, which is the same as before, force multiplied by perpendicular distance. So for the bending moment, we're going to analyze this from left to right. So from left to right, starting at RA. And from RA, we need to take the rotation or the moment about that point every single time. So right now we're at RA, and the only force that we're interested in is all the forces acting up to the point at RA to the left of it. So to the left of RA, we obviously have nothing. So therefore at RA, the bending moment at that point will be equal to 0. So for that, at RA, where we're at 0 meters, our bending moment is equal to 0. So we're going to go to the next point, and that point is going to be at our 4 meter mark. So at the 4 meter mark, we have right there that 5 kilonewtons we're talking about, right there at the 4 meter mark. And again, we're interested in all the forces that's acting to the left of the 4 meter mark. And to the left of the 4 meter mark, we only have one force, and that force is right there. That's our RA value. So we're going to find the bending moment using that RA value of 4.95 and its distance from the point that we are at, which is right there at that 4 meter. So its distance is just 4 meters. So what that calculation look like? So bending moment at 4 meter mark is just going to be 17.95. So that's the force to the left of our cutoff point. And that's going to be multiplied by our 4, which is the length. And that equals 71.80. So that force, we're taking it to be positive because it's rotating clockwise. So any other force that will be going counterclockwise will take it to be negative. So that calculation is done. So now on to the next point. So we're going now to that 19 kilonewtons mark. So I'm going to clear that, and we're now at right here at the 19 kilonewtons mark. And what we're interested in is any force acting to the left of that point right there. And at this point, we have only 2 forces acting to the left of that point, which is our 17.95 kilonewtons as well as our 5 kilonewtons. So let's do the calculation for that. So at that 7 meter mark, let's do our calculation. So once again, we have that reaction force, But now the distance of the reaction force to our cutoff point right there, our 19 kilonewtons meter mark, that distance is now 7 meters. So what we have now is 17.95 multiplied by the distance 7, because that's now increased because we've gone along further onto the beam. And the other force that we have now is that 5 kilonewtons, which it's 3 meters from our cutoff point, and it's trying to go in the opposite direction. So it means if we have taken this value to be positive, which we have, then if we're going in the opposite direction, which is now going to go counterclockwise, then this will have to be negative. So that's why we're having minus now this 5 multiplied by 3. And when we put that in the calculator, we have a final value of 110, so 110.65. So now we need to go on to the next point where force is acting, and that's going to move across now to our 8 kilonewtons mark. So right here is where we're interested in. I've just drawn that blue line down the middle where we're interested in. And what we're interested in is, again, all the forces acting to the left of that point. So let's do the calculation for that now. So to the left, we have our reaction force, 17.95. And again, its distance has now increased. So the distance is now 4 meters plus 3 meters plus that 9 meters. So we are now 16 meters away from that pivot point. Then we move to the 5 kilonewtons. That's the next force going in the opposite direction. Hence it will be negative. And its distance now increased as well to 12 meters. And then we have that 19 kilonewtons, which its distance is 9 meters. So let's put that into calculations. So what we now have is our first 17.95, and we know the distance already. We've established that it's 16 meters. And then we have our 5 newtons, which is trying to go in the opposite direction, and its distance is 12 meters. So 5 multiplied by 12. Then we have that 19 kilonewtons going again in the opposite direction. So we subtract that once again, and its distance is 9 meters. And our final sum here is going to be 56.2 kilonewton meters. So then that takes us on to the very last point. And that last point is the point where our second reaction is at, and that's at RB. Now, when we go all the way over to RB, that leaves us with everything acting to the left of RB, which is our 17.95, our 5 kilonewtons, our 19 kilonewtons, and our 8 kilonewtons. And if our system is in equilibrium, what we expect to get for this answer when we do all the bending moments together, we expect to get back at 0, because that's the case, especially when we have a pinned or a roller support. So let's do that. Let's just check our analysis to see if we get back at 0 with our calculations. And I'll do that one in this space just beneath here so you can see it as we go along. So first of all, we have that 17.95. And as you would expect, its distance is now increased. So that's now multiplying by 20. And we have minus that 5 kilonewtons. And again, its distance is now increased. So 9 plus 4 plus 3. So that's now 16. Minus our 8 kilonewtons. Minus our 19 kilonewtons. Again, our distance is now increased. And that distance is now multiplied by 13. Minus our 8 kilonewtons times 4. And when we sum all of this up, we should end up getting 0 kilonewtons meter. Okay. So that means our system is in equilibrium. And now that we have these points, all we need to do now is just to plot them so that we get the bending moment diagram. So let's do that now. So I have summarized our calculation so it's easy for us to make our plots. So now we're going to just make those plots and finish off nice and easy. So this is what we're going to draw our bending moment diagram on. And we just now need to plot our points and then draw our diagram. And our first point is at 0, 0. So right here, 0 meters with 0 kilonewtons, right there at the very start. Then we move across to the 4 meters, and it's going to be plotted at 71.80. And please note that this is just an estimation. So that's 7.180, somewhere thereabouts. Moving across now to 7 meters, that's going to go all the way up to 110. I'm just estimating here, just to give you an idea what the sketch should look like. Then we move across to 16 meters. That will be plotted at 56.2, so around there. And then we come back to 0. And now we're going to draw our lines to connect the points. So the first point connected, second point, the third, and now we get right back to 0. Now it's optional, but if you want, you can always shade your diagrams or whatever, fancy, but much tidier than this one. And there you have it. That's our bending moment diagram, our shear force diagram, and we've used our point loads on the simply supported beams to create both of those. So if you got any value from the video, please like the video, subscribe to the channel, and share this video to someone you think might need the help. And I'll see you in the next video.